Hello, everybody. This is Sunday, May 23rd, and we're about to enter our third week of our online astronomy course. Hope you're all doing well. And this week, we are going to be getting into some of the basic science of astronomy. You know, all astronomers can do is look at the stars, and yet you'll be finding out what the masses of the stars are, how big they are. And so how can we know this? And that's what this module and the next one are all about. In this module, you'll study forces and the way things move. And in the next module, you'll learn about light and all of the information we can get from light. Well, where did all this start out? And it started out, the first person to really understand how forces worked was Isaac Newton. And he was born in 1643 on Christmas Day, as it turns out. And he lived in this house right here behind me in Woolsthorpe, England. This is where he was born. I'll move aside here so you can see it a little bit better. I visited here in 2012. We were just driving around England, and it was a rainy day, and something we wanted to do wasn't going to work out, so we stopped by Newton's home in Woolsthorpe, England. And maybe you can see, if you look on the left side of your screen over there, there's an apple tree. Now, supposedly Newton was inspired to discover his law of gravity when he looked out one of the windows on this side of the house and saw an apple fall to the ground. And is that true or not? We really don't know. It's a good story, and Newton himself told it as though it were true. Now, it couldn't have been that apple tree that you see on the left side of your picture, because Newton couldn't have seen that from his window. But the tree that apple fell from is actually the tree that was standing right behind me as I was taking this picture. And there was a sign of it. The British government had posted a sign saying that this is the tree that the apple fell from, that Newton saw from his window. And you might be thinking, well, gosh, that's almost 400 years ago. How's that tree still around? And it turns out the tree blew down in a storm. And people thought it was dead, but there was still life in the roots, and the tree grew up again. So that's the very tree that Newton supposedly saw that apple fall from. And it was cool because it was, there were apples laying on the ground right at the base of it. So I just picked one up and ate it. That was sort of nice. But anyway, let's get back to our module here. And we're going to be learning about how Newton described motion. And he came up with 3 laws that described how things move. And his first law of motion says what a force does. Now, a force is just either a push away from you or something pulling towards you. So force is a push or a pull. But what does a force do? A force causes an object's motion to change. It causes that object to either speed up or slow down or change direction. And so that's what a force does. It causes motion of objects to change. And when I say objects, what am I thinking of? Well, I could be thinking of a tennis ball, a bowling ball, or stars. Stars move through space. And so I'm talking about all of those things. So a force causes something to speed up, slow down, or change direction. In other words, a force causes a change in an object's motion. Now, Newton's second law talks about how much an object's motion changes. And it relates a cause, which is a force, to a result, which is a change in motion, which we call an acceleration. An acceleration, as it's used in science, means either a speeding up, a slowing down, or a change in direction. So Newton's second law says force equals mass times acceleration, or maybe a little bit better, acceleration, an object's acceleration is the force divided by the object's mass. So, for instance, that just says that it's easier to push something light than something heavy. You know, if I'm going to if there's a bowling ball hanging from a rope in a room and I try to push that and get it moving, that's sort of hard to do. But if there's just a little light tennis ball, I can just boom, hit it, and it starts moving very easily. So that's Newton's second law. And Newton's third law is a law that describes how forces act on each other, how different objects exert forces on each other. And maybe you've experienced this. If you've ever been in a crowd trying to get through a doorway and they're trying to get through and you're pushing the people ahead of you and they're pushing you back. Well, that's Newton's third law. Newton's third law says, if I push you, then you push me back in the opposite direction just as hard. Same strength force, but opposite directions. And you know, you can demonstrate this to yourself if you get a rubber band. So here's a rubber band and I hook it around my thumbs and I stretch it out. And you know, no matter how I stretch this rubber band out or how I move my hands around or what I do, the force is always the same on my thumbs. If one pulls, if my right thumb pulls my left thumb in some direction, then my left thumb pulls just as hard on my right thumb in the opposite direction. And so you can get a rubber band and do this, and I can just amuse myself for hours doing this, but I won't take up the time now. And there's one other thing. Newton's great triumph as far as astronomy goes was his discovery of the law of gravity. Now, gravity is an attractive force, and it's an attractive force that acts between any two objects that have mass. So if there's two objects that have mass, then they attract each other through gravity. That means if there is somebody standing next to you, that by gravity, you are attracting them and they are attracting you. You know, this house behind me, you know, when I was there, it was attracting me and I was attracting it through gravity. But what's the biggest thing around? What's the most massive object around? That's the Earth. And so Earth is what creates the gravity that pulls us to the ground. You know, the gravity of the person next to you or the gravity due to this house are minuscule, ignorable compared to the gravity due to the Earth. And that has great importance for astronomy because gravity is what causes planets to move the way they do. The planets move around the sun in the way they do because of the sun's gravity. But you notice it's not really the sun's gravity, it's the gravity between the Earth and the sun. Both the Earth and the sun participate in setting up that gravity. And stars orbit other stars in space. Two stars can go around each other in space due to their mutual gravitational attraction. And in fact, you'll find out that that is how we can measure the masses of stars and how we can measure the mass of a planet going around a star. And so this is a very important part of astronomy. And in this module is where you'll be learning about Newton's laws of motion and his law of universal gravitation. Universal because it says that any object attracts any other object that has mass. Well, what else is there to take a look at in the sky this week? Well, there's a big deal, and I want to share the screen and show you what that is. I'm going to share the screen here. And let me get rid of that. And what there is a lunar eclipse starting this Wednesday morning, fairly early. Now, a lunar eclipse occurs when the moon moves through Earth's shadow, and this is going to be, just barely, but it will be, a total lunar eclipse. And so let me move this screen down a little bit. And the times I'll be showing you are for Ogden. But first, let me show you what's going to be happening. So I'll just start this little video in motion. And the white circles there are the Earth's shadow. There's the moon moving through the Earth's shadow. This is Earth's partial shadow, the penumbra it's moving through. And so now part of the moon moves through the blackest part of Earth's shadow. More and more of Earth's shadow sweeps over the moon. And now the moon is looking red as it passes through totality. And that's because all of the sunrises and sunsets on Earth go past the Earth and spill onto the moon. And because this is early in the morning, the moon sets before the eclipse is all over. So if you want to see this, when should you go out? And you can see here that on this Wednesday, May 26th, the eclipse begins. Let's see if I can go down a little bit. Here we go. Here's some better information. The eclipse begins at 2:47, but that's when it's just barely moving into Earth's partial shadow. So I wouldn't worry about that. The eclipse begins at 3:44, but still the moon isn't entirely into Earth's shadow yet. The total eclipse begins at 5:11 a.m. in the morning. And it only lasts for 14 minutes. It's over 5:25 in the morning. These are all Mountain Daylight Times. And if you're going to, get up to watch this, or if you're outside at that time to watch it, make sure you have a clear view of the southwestern horizon. It'll be in the southwest, and it's only going to be 8 degrees above the horizon. So make sure there's nothing in your way, because you really need the sun to see the moon, because it's going to be very low. But it's really something cool to see, a lunar eclipse, and that'll be happening this Wednesday, early in the morning. I figure if you're out there by 5 o'clock, you'll get to see the very best part of it. So hope you get to take advantage of that. So I will turn that off. And one more reminder, that is that this coming weekend is Memorial Day weekend. Memorial Day is the Monday the 31st. And because of that, I've postponed the due dates for modules 1, 2, and 3 to Tuesday, June 2nd. So just so you know, when everything is due, the quizzes for modules 1, 2, and 3 are going to be due on June 2nd. And that is the Tuesday after the Monday, which is Memorial Day. So I hope you have a good week. This is one of the more sciencey sort of chapters. There's some math in here. And as with all the math, I put most of the math on the homework quizzes, and no math really at all on the exams. That's because I want you to see how astronomers come up with the results that they get. How do we get these numbers we get for masses and the sizes of stars and the sizes of galaxies? And where's all that come from? I just want you to see what that math looks like. But on the exams, I'll do all the math for you. And all I'll ask you to do is ask, is this the way to do it? And so you won't need a calculator on any of the exams. And so I wouldn't worry about that at all. As always, if you have a question, please send me an email. I'll be happy to set up a Zoom meeting if you have any questions. If you have any problems accessing anything having to do with the course, if you can't get Stellarium to work or something like that, please let me know, and I'll do my best to get that straightened out too. So enjoy learning about Newton's laws, And I will see you next time. And until then, bye-bye.